There are places in the universe where almost nothing exists. No bright galaxies, no glowing nebulae, no familiar patterns of stars. Only an enormous darkness stretching across hundreds of millions of light years. These regions are called cosmic voids, and most of them formed naturally as gravity pulled matter into galaxies, clusters, and the vast filaments of the cosmic web. But one void appears so immense, so empty, and so strangely isolated that it seems to push our understanding of the universe to its limits. Inside it, galaxies are separated by distances almost impossible to imagine. If the Milky Way existed near its center, ancient astronomers might have believed our galaxy was completely alone. The surrounding universe could have remained invisible for generations. How did such an enormous emptiness form? Why is there so little matter inside it? And could something hidden within that darkness explain why this region appears so unnatural? Before we begin, tell us in the comments where you are watching from and what time it is in your city right now. And if you enjoy calm journeys into the deepest mysteries of space, subscribe to Theories Before Sleep. Tonight, we travel beyond the crowded galaxies, toward the most terrifying void in the known universe, a place where the universe seems to disappear. From Earth, the universe appears crowded. On a clear night, thousands of stars seem to cover the sky. Through a telescope, the darkness becomes even richer. Faint galaxies emerge between the stars. Nebulae glow inside the Milky Way. Clusters appear as delicate clouds of light, each one containing suns too distant to separate with the eye. The deeper we look, the more crowded space seems to become. One galaxy behind another, one cluster beyond another, light continuing almost without end. It creates the impression that the universe is evenly filled, that matter has been scattered throughout space like dust across an infinite floor. But that is not what the universe truly looks like. When astronomers began measuring the distances to enormous numbers of galaxies, a hidden structure slowly appeared. Galaxies were not distributed randomly. They gathered into chains, walls, filaments, clusters, enormous streams of matter stretching across hundreds of millions of light years. Between those structures were dark regions containing far fewer galaxies. The universe began to resemble a web, a cosmic web. Its bright filaments are made from galaxies, gas, and dark matter pulled together by gravity. At the places where several filaments meet, immense galaxy clusters form. These intersections contain thousands of galaxies, hot clouds of gas, and quantities of dark matter far greater than anything visible. But between the filaments lie the voids, vast underdense regions where matter is scarce. They are not small gaps between neighboring galaxies. They are enormous volumes of space that can extend across tens or even hundreds of millions of light years. Some are almost spherical. Others are stretched between filaments. Some contain faint chains of galaxies running through them. Others appear almost completely empty. Together, voids occupy most of the volume of the universe. The stars, galaxies, and clusters that seem to dominate astronomy are concentrated into a relatively small part of cosmic space. Most of the universe is not filled with luminous structures. Most of it is darkness between them. This arrangement began with tiny imperfections in the early universe. Shortly after the beginning of cosmic history, matter was distributed far more evenly than it is today. There were no mature galaxies, no clusters, and no vast empty regions like the ones we now observe. But the universe was not perfectly smooth. Some places contained slightly more matter, others contained slightly less. The The differences were incredibly small, but gravity had billions of years to amplify them. Regions with a little more matter created slightly stronger gravitational attraction. They pulled in additional gas and dark matter. As more material arrived, their gravity increased, allowing them to pull in still more. The rich became richer. Dense regions grew into the first structures. Dark matter gathered into invisible frameworks. Gas fell into those frameworks, heated, cooled, and eventually formed stars. Small galaxies appeared. Galaxies merged. Clusters grew. Filaments stretched between the densest regions. But gravity was also changing the less crowded areas. Matter near an underdense region was gradually drawn toward denser surroundings. It moved toward the walls and filaments forming around the emptiness. The underdense region lost material. As matter left, the region became even emptier. The void expanded. This is an important detail. Cosmic voids are not simply places where matter never existed. They are regions from which much of the matter has been pulled away. Gravity has been quietly emptying them for billions of years. Galaxies near the boundaries move toward denser structures. Gas follows the gravitational landscape. The void grows larger, while the surrounding cosmic web becomes more defined. In this sense, voids are active parts of the universe. They evolve, they expand, they influence the motion of nearby galaxies. They press outward as the denser structures around them pull material away. The universe is not only being shaped by where matter gathers, it is also being shaped by where matter disappears. Most cosmic voids fit naturally into this picture. Their sizes and populations can be compared with computer simulations. Their shapes reveal how structures evolved. Their galaxies offer a quiet environment where astronomers can study what happens when a galaxy forms far from crowded clusters. But one region became famous because its scale seemed almost unreasonable. In the direction of the constellation Boötes, hundreds of millions of light years from Earth, astronomers found an enormous volume with remarkably few galaxies. It became known as the Boötes Void, and sometimes, more dramatically, the Great Nothing. The discovery began not with a photograph of darkness, but with measurements. A dark region in the sky does not automatically reveal a cosmic void. A void is not a black object that can be photographed directly. The night sky is already dark, and galaxies at different distances overlap from our perspective. To discover a void, astronomers must build a three-dimensional map. They observe galaxies. They study their light. They measure how much the universe's expansion has stretched that light toward longer, redder wavelengths. This stretching is called redshift. Redshift allows astronomers to estimate how far away a galaxy is and place it within a map of cosmic structure. When enough galaxies are measured, patterns begin to appear. Dense clusters become visible, filaments emerge, and sometimes enormous gaps open between them. In 1981, astronomers studying galaxy redshifts in the direction of Boötes reported something extraordinary. They were seeing galaxies on the near side of a huge region. They were seeing galaxies beyond it, but inside the region, very little appeared. The gap was not the result of a small dark cloud blocking the view. It was not a failure of the telescope. It was not simply a region where galaxies were too faint to detect. The three-dimensional map suggested that a truly enormous volume of space contained surprisingly few large galaxies. Later surveys confirmed the broad picture. The Boötes Void is often estimated to be roughly 250 to 330 million light-years across, depending on how its boundaries are defined. Even the lower estimate is almost impossible to imagine. light could cross Earth in a fraction of a second. It takes a little over 1 second to travel from the Moon to Earth. It takes more than 8 minutes to arrive from the Sun. It takes about 4 years to reach us from the nearest star beyond the Sun. It takes roughly 100,000 years to cross the Milky Way. But to cross the Boötes Void, light itself could require hundreds of millions of years. If a beam of light entered one side of the void during the age of the earliest dinosaurs on Earth, it might still be traveling through the region today. Human beings have difficulty understanding this scale because nothing in ordinary experience resembles it. A desert can feel empty, but its opposite edge may be visible. An ocean can isolate a ship for days, but another coastline eventually appears. Interstellar space can separate stars by several light years. The Boötes Void separates major concentrations of galaxies across a distance far greater than the width of our entire galaxy. Imagine shrinking the Milky Way until it became the size of a small coin. On that scale, the Boötes Void would still extend far beyond the room containing it. It would swallow the building, the streets outside, and much of the surrounding landscape. The galaxy would become a speck inside an absence too large to understand from within. This leads to one of the most unsettling questions about the void. What would the universe look like if the Milky Way were located near its center? Our night sky would still contain stars, because those stars belong to our own galaxy. The band of the Milky Way would still cross the darkness. Nearby nebulae would still glow. Planets would still move through the solar system. But beyond our galaxy, the universe would appear almost empty. The great galaxy clusters studied by modern astronomers would be far more distant. Neighboring galaxies might be extremely faint. The broader cosmic web could remain hidden from early telescopes. For much of human history, people might reasonably conclude that the Milky Way was alone. Even after astronomers learned that the Milky Way was a galaxy, proving that other galaxies existed could have taken much longer. Our understanding of the universe depends partly on our location. We live in a region where other galaxies are visible. The Andromeda Galaxy can be seen without a telescope under dark conditions. Nearby groups and clusters allow us to recognize that the Milky Way is only one member of a much larger population. Inside a deep void, the evidence would be weaker. A civilization could study the stars for centuries without realizing that most matter in the universe had gathered into structures far beyond its observable neighborhood. The universe would not actually be empty, but from inside the void, it might feel that way. This is one reason the Boötes Void is so haunting. It is not merely a dark region seen from the outside. It is a place where the universe itself would seem fundamentally different to anyone living within it. Yet the name Great Nothing can also be misleading. The void is not absolutely empty. Galaxies have been detected inside it. Some are isolated. Some form small groups. Some appear arranged in thin structures passing through the emptiness. There is also gas. There is dark matter. There are particles. There is radiation left from the early universe. There may be countless faint dwarf galaxies that remain difficult to observe. Even the emptiest cosmic void is not a perfect vacuum. Space itself contains fields, particles, and energy. The darkness is never completely empty. But emptiness in astronomy is relative. A region does not need to contain nothing to be considered a void. It only needs to contain far less matter than the cosmic average. Imagine looking at a continent from high above at night. Cities form bright clusters. Roads connect them like filaments. Between them lie dark rural areas. Those dark areas are not truly empty. They contain houses, fields, rivers, and small towns. But compared with a major city, their density is extremely low. Cosmic voids are similar, except the roads are made from galaxies, the cities are clusters, and the distances are measured in millions of light years. The few galaxies inside the Boötes Void are therefore not evidence that the void does not exist. They make the region even more interesting. How did those galaxies form with so little surrounding matter? Did they begin inside the void? Were they left behind as the region expanded? Are they remnants of faint filaments that once carried more material? Do they evolve differently from galaxies in crowded environments? A galaxy inside a void lives a quiet life. It experiences fewer close encounters. It is less likely to collide with another large galaxy. It receives less material from surrounding filaments. Its growth may be slower. Its shape may remain undisturbed for long periods. In a rich cluster, galaxies pass near one another. Gravity stretches them. Gas is stripped away. Collisions and mergers reshape them. Inside a void, millions of years can pass with almost nothing nearby. A galaxy may rotate beneath a sky containing no other bright galaxy visible to the naked eye. Its stars are born, age, and die in isolation. Its planets orbit beneath a cosmos that appears nearly abandoned. And yet, these galaxies are not completely disconnected. Gravity still acts across the void. The large-scale expansion of the universe continues. Matter still follows subtle structures of dark matter. Thin tendrils may connect galaxies too faintly for us to map completely. What appears empty from a distance may contain delicate architecture, a hidden web within the larger emptiness. The Boötes Void may therefore be less like a perfectly cleared sphere and more like a collection of neighboring underdense regions that expanded and merged over time. Smaller voids can grow together. The thin walls between them may lose matter. Their boundaries become less distinct. Eventually, several empty regions can resemble one gigantic void. This may help explain why Boötes became so large. It may not have formed as a single impossible cavity. It may be the result of many smaller absences combining over cosmic history, like bubbles joining beneath the surface of water. At first, each bubble has its own boundary. When they touch, the wall between them thins. Then it disappears. A larger bubble remains. The universe may create enormous voids through a similar hierarchy. Small, underdense regions form within larger, underdense environments. They expand. They merge. Their matter moves towards surrounding filaments. After billions of years, what remains is a vast volume containing only scattered galaxies and faint internal structure. This means the Boötes Void does have possible explanations within modern cosmology. It is not a supernatural wound in space. It is not evidence that part of the universe has been removed. It is not a region where the laws of physics have stopped working. But its size still raises difficult questions. How rare should a void this large be? How empty is it when faint galaxies and dark matter are included? Where exactly do its boundaries begin? Is it truly one coherent structure, or several connected voids seen as one? Can the standard history of cosmic structure produce regions like this easily, or only under unusual starting conditions? These questions matter because voids preserve information. Dense clusters have experienced billions of years of collisions, mergers, shocks, and gravitational disturbance. Their history is complicated. Voids are quieter. Because they contain less matter and undergo fewer violent interactions, they can retain a cleaner record of the conditions from which they formed. Studying them allows astronomers to test the behavior of gravity across enormous distances. Voids may reveal how dark matter is distributed. They may help measure the expansion of the universe. They may even offer clues about dark energy, the unknown influence associated with the accelerating expansion of cosmic space. Dark energy does not gather matter into structures. Its influence becomes most noticeable across the largest scales and emptiest regions. In dense clusters, gravity dominates. Inside voids, where gravity from matter is weaker, cosmic expansion plays a more visible role. Voids may expand faster than denser parts of the cosmic web. Their interiors become increasingly empty, while their boundaries move apart. In the distant future, if cosmic expansion continues accelerating, these regions may grow more isolated. Galaxy clusters will remain gravitationally bound, but the space between them will widen. Distant galaxies will move beyond one another's observable horizons. The universe will gradually become darker for every isolated group. In that sense, cosmic voids offer a preview of the universe's possible future, a future where light from distant structures no longer arrives, where galaxies exist in isolated islands, where most of the cosmos becomes unreachable and unseen. The Boötes Void feels terrifying, not because it contains a known monster. There is no evidence of a gigantic black hole hidden at its center. No invisible object has consumed its galaxies. No force field surrounds it. Its terror comes from absence. Human beings are accustomed to fearing things. Storms, predators, fire, collisions. The void represents a different kind of fear. The fear that there may be nothing nearby, nothing answering, nothing interrupting the darkness for hundreds of millions of light years. Imagine a spacecraft capable of traveling at the speed of light. Such a craft is impossible for any object with mass, according to our current understanding. But imagine it only as a way to feel the distance. The ship enters the Boötes Void. Earth disappears behind it. The galaxies at the boundary slowly fade. Years pass. Then, centuries. Then, millions of years. The ship continues moving at the fastest speed permitted by nature, yet it remains inside the void. Entire species could evolve and vanish on distant planets while the journey continued. Mountain ranges could rise and erode. Stars could be born. Other stars could die. Still, the ship would not reach the opposite side. There might be isolated galaxies along the route, but they would be rare islands in an ocean beyond comprehension. Even light cannot make the crossing quickly. That fact transforms the void from a distant astronomical object into something deeper. It becomes a measure of how large the universe has become. The Boötes Void is hundreds of millions of light years away, which means we also see it as it existed hundreds of millions of years in the past. The light reaching our telescopes began its journey long before humans existed. We cannot observe what the void looks like at this exact moment. We see an ancient version. Its galaxies have continued evolving. Its structure has continued expanding. The void we study is already a ghost of itself. This is true of everything in astronomy. To look across space is to look backward through time. But in the Boötes Void, the effect feels especially powerful. We are studying emptiness preserved in old light, a dark region from a universe younger than the one surrounding us now. And perhaps the most unsettling truth is that the Boötes Void is not unique in being empty. It is only one dramatic part of a universe dominated by voids. There are other enormous underdense regions, other dark volumes between the filaments, other places where galaxies become rare and the cosmic web thins toward invisibility. The universe we imagine as filled with stars is mostly space where stars are absent. The bright structures are exceptions. The emptiness is the rule. Our galaxy exists in a filament. Our solar system exists inside a galaxy. Earth exists beside a star. Life began in a rare concentration of matter, surrounded by increasingly larger layers of darkness. A planet inside a solar system inside a galaxy inside a group near larger structures, and beyond them, voids, immense regions where the architecture of the universe opens into silence. So the Boötes Void is not terrifying because it should not exist. It is terrifying because it reveals what the universe has always been. Matter gathering into small islands, light confined to narrow filaments, everything familiar surrounded by distances too great to cross. But one mystery remains. If the void formed through ordinary cosmic evolution, why did this particular region become so enormous? Was it created by several smaller voids merging? Does it contain more hidden structure than our surveys can detect? Could faint galaxies and dark matter reveal that the emptiness is partly an illusion? Or does the great nothing preserve evidence of something unusual in the early universe? To understand that, we must leave the visible galaxies behind. We must enter the void itself and discover what remains when almost everything has been taken away. To understand what makes a cosmic void so unsettling, we must imagine leaving the bright structures behind, not merely looking toward the darkness from a safe distance, but entering it. A spacecraft traveling toward the Boötes Void would not cross a visible wall. There would be no boundary marked by a sudden change in color, no curtain of darkness, no moment when the stars vanished all at once. The transition would be gradual. At first, the surrounding universe would still appear familiar. Galaxies would lie in many directions. Clusters would glow in the distance. Thin chains of light would trace the filaments of the cosmic web. But as the journey continued, those structures would begin to gather behind the spacecraft. Ahead, the gaps between galaxies would widen. The nearest large galaxies would become more distant. The sky would not become completely black because distant light from beyond the void would still arrive. But the depth of that darkness would change. The surrounding universe would feel less immediate, less connected. The bright architecture of the cosmic web would seem to retreat toward the horizon. Eventually, the spacecraft would enter a region where the nearest major galaxy might be separated from it by millions of light years. In ordinary intergalactic space, galaxies are already widely separated. But within a cosmic void, the isolation becomes more extreme. The emptiness is not only the absence of stars, it is the absence of places where stars are usually born. There are fewer galaxies, less gas, less dark matter, fewer collisions, fewer gravitational encounters, fewer of the processes that keep the universe visibly active. A human observer inside such a spacecraft might look outward and feel that the universe had stopped, but it would not be truly empty. Even within the deepest void, matter remains. There are atoms, sparse hydrogen, occasional helium, weak magnetic fields, low-energy particles, radiation traveling from distant galaxies, the ancient microwave glow left behind by the early universe. There may be dark matter spread thinly through the region, forming a barely detectable skeleton beneath the visible emptiness. And there are galaxies, not many, but enough to reveal that even the great nothing contains structure. Some void galaxies appear isolated, others form pairs, a few gather into narrow chains. These arrangements suggest that the cosmic web does not disappear completely inside a void, it becomes faint. Imagine a spiderweb stretched across a dark room. Under bright light, every strand is visible. Lower the light, and the thinnest threads disappear first. Only the strongest lines remain. Lower it further, and even those begin to vanish. The web is still there, but almost nothing reveals it. The interior of a cosmic void may be similar. The largest filaments define the walls outside. Inside, thinner tendrils of dark matter and gas may connect scattered galaxies. These delicate structures are difficult to observe because they contain so little luminous matter. The void may therefore hold a hidden network, a weaker version of the cosmic web inside the greater web. Galaxies forming along threads too faint for most surveys to see. This possibility changes the meaning of emptiness. The Boötes Void may not be an empty bubble. It may be a shadowed landscape, a place where structures exist below the threshold of our instruments. Astronomers face a difficult problem when trying to measure emptiness. They can only count what their telescopes can detect. A large, bright galaxy can be seen across enormous distances. A small, dim galaxy is much easier to miss. A galaxy containing billions of stars may still appear as a faint point of light if it is far away. A dwarf galaxy containing far fewer stars may vanish entirely against the background. This means that every map of a distant void is incomplete. The emptiness we see is partly real, and partly a limit of observation. There could be many faint dwarf galaxies inside the Boötes Void. Some may contain almost no new stars. Some may be dominated by dark matter. Some may hold clouds of gas that have never collapsed efficiently enough to produce much visible light. A galaxy does not need to shine brightly to exist. If it contains only a small number of stars spread across a wide region, it can become almost transparent. Even within our own cosmic neighborhood, astronomers continue discovering extremely faint galaxies that remained hidden for years. Inside a void, hundreds of millions of light-years away, the challenge becomes far greater. A small galaxy could disappear into darkness. Its stars too faint, its gas too diffuse, its light stretched and weakened by distance. For this reason, the Boötes Void may contain more galaxies than early estimates suggested. But even if hundreds of faint systems remain undiscovered, the region would still be deeply underdense. The mystery does not require absolute emptiness. It comes from scale. A volume so large should normally contain far more matter. The question is not why there are 0 galaxies. The question is why there are so few. One possible answer lies in dark matter. Dark matter cannot be seen directly because it does not emit or reflect light in the ordinary way. Yet its gravity shapes galaxies, clusters, and the cosmic web. Most of the matter in the universe appears to be dark. The stars, planets, gas clouds, and everything visible represent only a minority. This means that a cosmic void is not defined only by a lack of galaxies. It also contains less dark matter than average. The invisible framework itself is thinner. That has enormous consequences. Galaxies form where dark matter gathers into dense halos. Gas falls into these halos. The gas cools. Stars form. A visible galaxy emerges inside an invisible gravitational structure. But inside a void, dark matter halos tend to be smaller and rarer. There are fewer deep gravitational wells. Gas has fewer places to collect. Star formation becomes less efficient. The region remains dark not because something destroyed its galaxies, but because the conditions required to build large galaxies were never as strong there. In the early universe, the Boötes region may have begun with only slightly less matter than the cosmic average. The difference would have been tiny, perhaps only a fraction of a percent. But over billions of years, That small shortage grew. Nearby dense regions pulled matter outward. Dark matter moved toward surrounding filaments. Gas followed. The underdense region expanded. The potential sites for galaxy formation became increasingly rare. A microscopic difference in the early universe became an emptiness hundreds of millions of light years wide. This is one of the most profound ideas in cosmology. The largest structures in existence grew from incredibly small imperfections. The cosmic web did not need a designer. It did not require giant explosions carving holes into matter. Gravity slowly amplified what was already there. A slightly denser region became a cluster. A slightly emptier region became a void. Time did the rest. But the Boötes Void may still be unusually large even within this natural process. To explain it, astronomers often consider the possibility that it is not one simple void. It may be a supervoid, a larger underdense region assembled from several smaller voids. This process can be imagined as a landscape of bubbles. In the early stages, each underdense region expands separately. Matter moves away from the centers and gathers along the boundaries. The walls between neighboring voids become crowded with galaxies, but if those dividing walls are weak, their matter may continue moving toward larger structures farther away. The walls thin, the smaller voids connect. Over time, several neighboring regions become one enormous underdense complex. The result can appear like a single gigantic cavity, but internally, it may contain subtle divisions, faint galaxy chains, weak walls, small groups marking the remains of boundaries that once separated smaller voids. Some of the galaxies observed inside the Boötes Void may lie along such remnants. They may not be randomly scattered. They may trace the fragile internal architecture of a merged void system. If this is true, the Great Nothing is not one whole. It is a graveyard of smaller boundaries, a region where several empty spaces gradually consume the structures between them. The idea is less mysterious than a cosmic cavity appearing all at once. But it is no less strange to imagine. Entire walls of galaxies becoming so weak that the surrounding emptiness effectively joins together. The void growing not by swallowing matter violently, but by allowing gravity to carry the matter away. Cosmic voids do not expand like explosions. Nothing pushes their boundaries outward from a central blast. Instead, they grow, because the surrounding universe pulls matter away. This creates the appearance of outward motion. Galaxies near the edge of a void tend to move toward the dense walls and filaments beyond it. From the perspective of the center, everything seems to be receding. The emptiness becomes larger. Its internal density falls. The process continues for billions of years. In a universe without dark energy, gravity would still create voids. But dark energy adds another influence. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. It does not act like an ordinary force that can be collected or shielded against. It appears to be associated with space itself. As the universe expands, dark energy becomes increasingly important across enormous distances. Voids are especially useful for studying it because they contain less matter. In dense regions, gravity from galaxies and dark matter dominates local motion. Inside voids, there is less gravity pulling structures together. The expansion of space becomes easier to detect. Some cosmologists describe voids as places where dark energy has a clearer stage. Not because dark energy is stronger there in a simple local sense, but because less matter exists to oppose the expansion. As a result, voids may expand more rapidly than the cosmic average. their density continues falling. Their boundaries move farther apart. The darkest regions of the universe become even darker. This means the Boötes Void is not a finished object. It is still evolving. The light reaching us shows the void as it existed hundreds of millions of years ago. Since then, the galaxies within it have moved. The surrounding filaments have shifted. The underdensity has continued changing. The void we would encounter today may be slightly larger than the ancient version recorded in the light now reaching Earth. We can never observe it exactly as it is at this moment. By the time its present-day light reaches us, Earth will exist far in the future. Every distant structure is hidden behind time, but emptiness makes this fact feel sharper. When we look at a galaxy, we see old stars. When we look into a void, we see old absence, a region where little happened, preserved across hundreds of millions of years. Could something massive be hidden in the center? This possibility appears often in speculation. Perhaps an enormous black hole removed the galaxies. Perhaps a mysterious object sits invisibly within the darkness. Perhaps the void is not empty at all, but filled with something that does not produce light. These ideas are compelling because humans expect emptiness to have a cause. When a forest contains a circular clearing, we look for fire. When a wall contains a hole, we look for damage. When a map of the universe contains a vast gap, we imagine something must have cleared it. But there is no evidence that a giant object created the Boötes Void. A black hole powerful enough to remove matter from a region hundreds of millions of light years across would create enormous gravitational effects. Galaxies near the void would move toward it. Light passing nearby would bend. The surrounding cosmic web would reveal the mass. Instead, galaxies appear to move away from the underdense interior and toward denser structures. This is the opposite of what a hidden massive object would produce. The void is not empty because something inside pulled matter inward. It is empty because there was too little matter there to begin with, and surrounding gravity pulled much of what remained outward. The center of the void is not a gravitational monster. It is a gravitational weakness. A region with less ability to hold matter. This weakness is difficult to picture because gravity is usually understood through attraction. We imagine objects pulling other objects toward them. But in a universe filled unevenly with matter, a region containing less mass can influence motion through what it lacks. Galaxies are pulled more strongly toward dense areas than toward the void. The result is motion away from the emptiness. Sometimes astronomers describe this as if the void were repelling matter. But the void does not possess an anti-gravity force. It is not pushing. The dense surroundings are pulling more strongly. Imagine standing between two groups of people holding ropes attached to you. One group is very large. The other contains only a few people. You move toward the larger group, not because the smaller group pushes you away, but because its pull is weaker. The cosmic void acts in a similar way. Its lack of mass helps shape the motion of galaxies around it. This raises another unsettling possibility. Our own galaxy may be influenced by nearby underdense regions. The Milky Way does not sit inside the Boötes Void, but our local cosmic environment includes smaller voids. The motion of our galaxy and neighboring galaxies is shaped not only by dense clusters pulling us, but by empty regions failing to pull us back. The universe's large-scale motion is created through a balance of attraction and absence. Galaxies move because of what exists, and because of what does not. This makes voids essential to understanding the cosmic web. They are not leftover spaces between important structures. They are structures themselves. A void has a shape, a boundary, an internal density, an expansion rate, a gravitational influence. It can collide and merge with other voids. It can push matter toward walls indirectly. It can affect the growth of galaxies around its edges. The darkness has architecture. One of the most revealing places in any void is its boundary. At the edge, matter swept from the interior gathers into walls and filaments. Galaxy density rises. Gas becomes more abundant. Dark matter halos grow larger. The transition can create striking contrasts. Inside the void, galaxies are rare. Near the wall, they become numerous. Clusters may sit where several walls meet. From a great distance, the void resembles a dark cavity surrounded by light. But from inside, the wall might appear as a faint, distant concentration of galaxies. A ring of structure around an enormous interior. The galaxies near void boundaries can experience a different history from those deep inside. They may receive gas flowing toward the filaments. They may interact with neighbors more often. They may grow larger. The interior galaxies remain isolated and starved of fresh material. Over time, the contrast increases. The wall becomes richer. The center becomes poorer. The cosmic web sharpens. If an advanced civilization existed in a void galaxy, the boundary would represent the nearest direction of abundance. It might look toward the distant wall, as humanity once looked toward unknown continents, a place filled with galaxies, resources, possible life. But reaching it would be almost unimaginable. Even a civilization capable of traveling between stars would remain trapped within its local galaxy. Intergalactic travel requires crossing millions of light years. Crossing the entire void would require hundreds of millions. The civilization could understand the wall, map it, observe it, receive ancient light from it, but physical contact might remain impossible forever. This is isolation on a scale beyond loneliness. A civilization could know that the universe was crowded elsewhere while being unable to reach any of it. Its radio signals would expand through the void at the speed of light. After 1,000 years, they would cover 1,000 light years. After 1 million years, 1 million light years. Still only a small fraction of the void. Even a message sent at light speed could require hundreds of millions of years to cross the region. By the time it arrived, the civilization that transmitted it might be gone. Its planet altered, its star dead, its galaxy transformed. The message would continue traveling through darkness after the sender no longer existed. This is the deepest silence of the void, not the absence of sound. Sound cannot travel through ordinary vacuum anyway. The silence comes from distance, a separation so enormous that communication loses meaning. A reply might return long after both civilizations had vanished. Inside the boat's void, intelligence could exist without ever knowing another intelligence in real time. Two societies might detect each other's ancient light, each one seeing the other as it was millions of years ago, each sending messages toward a past that can never answer immediately. They would share the same universe, but never the same moment. And yet, the void could contain planets. Its galaxies contain stars. Those stars may have worlds. The low density of the surrounding region does not prevent planetary systems from forming inside an existing galaxy. Once a galaxy has enough gas and heavy elements, stars and planets can develop much as they do elsewhere. There could be oceans inside the great nothing, atmospheres, weather, life, cities, entire histories unfolding in galaxies that appear as faint points from Earth. The void is empty only on the cosmic scale. Locally, one of its galaxies could contain billions of stars. A planet inside it might feel no different from Earth. The sky would contain constellations made from nearby suns. Its inhabitants would see moons, planets, nebulae, and the band of their own galaxy. Daily life would not feel like life inside an abyss. Only when their astronomers looked beyond the galaxy would the isolation become clear. They would discover that their island of stars was surrounded by an ocean far larger than expected. Perhaps their earliest cosmology would imagine that their galaxy was the universe. Perhaps distant galaxies would remain undiscovered until technology became extraordinarily advanced. When the first external galaxy was finally detected, it might be celebrated as proof that their world was not alone in the darkness. But then, the distance would be measured, and the discovery would become both hopeful and cruel. Others exist, but almost impossibly far away. This is why the void is frightening even without any unknown object inside it. It forces us to confront a form of separation that technology may never overcome. Humans often imagine that enough progress can solve any distance. Faster engines, longer lives, artificial intelligence, generation ships. But cosmic voids make even the most ambitious dreams seem small. A generation ship might cross several light years. A civilization lasting millions of years might spread through a galaxy, but hundreds of millions of light years represent a different category of problem. Expansion of space itself becomes important. Destinations continue moving. Energy requirements become overwhelming. Time becomes the dominant barrier. The void does not need walls to imprison anyone. Distance is enough. Still, the emptiness may contain information more valuable than any hidden object. Because voids formed from the earliest patterns of matter, their shapes preserve clues about the young universe. Their distribution can be compared with simulations. Their expansion can test theories of gravity. Their galaxies can reveal how star formation changes in isolation. Their boundaries can show how dark matter shapes the cosmic web. The Great Nothing may have an explanation, but understanding it completely could reveal whether our explanation of the entire universe is correct. If simulations consistently fail to produce voids as large or empty as boats, something may be missing. Perhaps the initial conditions were more unusual than expected. Perhaps dark matter behaves differently on very large scales. Perhaps gravity requires modification. Perhaps the void is not one structure at all. Or perhaps our observations remain too incomplete to see its true population. The frightening possibility is not that the void breaks physics. It is that we do not yet know whether it does. From a distance, it appears as an absence. But inside that absence are tests of dark matter, dark energy, galaxy formation, gravity, and cosmic history. The void is a question written in darkness, and to answer it, astronomers must search for what is hardest to observe. Not the brightest galaxies, the faintest ones, not the densest clusters, the weakest structures, not the places where matter gathered, the places it abandoned. The boat's void appears silent because its signals are faint, its galaxies are dim, its gas is thin, its dark matter is invisible. Its scale is too large to understand at once. But silence is not the same as emptiness. There may be patterns inside it we have not yet mapped. Filaments too delicate to see. Dwarf galaxies below our detection limits. Ancient gas clouds that never formed stars. Planetary systems orbiting isolated suns. Perhaps even life looking outward from one small galaxy. wondering why the rest of the universe seems so far away. The great nothing is not terrifying because nothing exists there. It is terrifying because something may exist there, surrounded by distances so vast that it might remain alone forever. The deeper astronomers study the great nothing, the more difficult the simplest question becomes. How empty is it really? At first, this sounds easy to answer. Count the galaxies, measure the volume, compare the result with an ordinary region of the universe. But cosmic voids do not have solid walls. There is no bright border showing where one ends and another begins. A void fades gradually into the structures around it. Galaxy density rises slowly. Thin filaments appear. Small groups become more common. Eventually, the emptiness becomes part of the cosmic web again. Different definitions can therefore produce different sizes. One astronomer may define the void using only large, bright galaxies. Another may include faint dwarf galaxies. A third may divide the same region into several smaller voids, connected by narrow passages. The object remains the same, but the map changes. This is one reason estimates for the Boötes Void vary. Its boundaries depend partly on what we choose to count. If only the brightest galaxies are used, the region appears enormous and almost cleanly empty. If smaller galaxies and faint internal structures are included, the void begins to look more complicated. It may contain thin chains, small groups, weak walls left behind by earlier stages of cosmic evolution. But complexity does not make the void disappear. Even after more galaxies are added, the region remains deeply underdense. There is still far less matter than expected across an extraordinary volume. The uncertainty lies not in whether the void exists, but in precisely what kind of void it is. Perhaps it is a single vast structure. Perhaps it is several neighboring voids forming one connected underdense region. Perhaps it contains a hidden internal web too faint for current surveys to reveal completely. Or perhaps its emptiness is more extreme than our standard models produce comfortably. This uncertainty is where the mystery begins. Modern cosmology has a remarkably successful description of how structures form. The model begins with a young universe filled with small variations in density. It includes ordinary matter, dark matter, radiation, the expansion of space, and dark energy. Computers can take these ingredients and create simulated universes. Inside those digital universes, matter gathers into halos. Gas falls into gravitational wells. Galaxies form. Clusters grow. Filaments connect. Voids open between them. When astronomers compare these simulations with the real universe, the overall resemblance is extraordinary. The cosmic web appears naturally. Large voids appear naturally. Even the way galaxies line the walls of voids can be reproduced. This means the existence of the Boötes Void is not by itself a violation of cosmology. The universe knows how to create emptiness. The difficulty is statistical. How often should a void of this size appear? How empty should its interior become? How many similar structures should exist within the volume we can observe? A very large void may be rare without being impossible. This distinction matters. Imagine shuffling a deck of cards and dealing an unusual sequence. If 5 cards appear in perfect order, the result is surprising, but it does not prove the deck is broken. Rare events occur when enough opportunities exist. The observable universe contains an enormous number of galaxies and a tremendous volume of space. Even a structure that forms only under uncommon conditions may appear somewhere. The Boötes Void may simply be one of the largest examples available for us to see. We notice it because it is extreme. There may be no need for unknown physics. But to know whether it is merely rare, astronomers must calculate how rare. And that is not simple. Simulations have limited resolution. A simulated universe must be large enough to produce structures hundreds of millions of light years across. At the same time, it must contain enough detail to track small galaxies inside those structures. Increasing scale often reduces detail. Increasing detail requires more computing power. Researchers must make choices about which physical processes to include and how accurately to represent them. Star formation is complicated. Supernova explosions move gas. Black holes release energy. Radiation heats matter. Galaxies lose and gain material. These processes affect which dark matter halos become visible galaxies. A simulation may contain many small halos inside a void, yet only a few may produce enough stars to be detected. The apparent emptiness, therefore, depends not only on gravity, but also on how galaxies light up. This creates a hidden distinction. A void of galaxies is not necessarily a void of matter. Some dark matter halos may exist without bright galaxies. Some may hold small amounts of gas, but almost no stars. Some may have formed stars early and then faded. Others may never have gathered enough material to ignite visibly. The map created from starlight is therefore incomplete. It shows where luminous matter exists. It does not show everything gravity has built. To reveal the dark structure, astronomers need other methods. One method uses gravitational lensing. Mass bends space. Light traveling past that mass changes direction slightly. Dense galaxy clusters create obvious lensing, sometimes producing stretched arcs and multiple images of background galaxies. A void creates the opposite kind of effect. Because it contains less matter than average, light passing through it is focused less strongly than light passing through a typical region. The result is extremely subtle. Background galaxies may appear slightly changed in shape or brightness. No single galaxy provides enough evidence. Astronomers must examine many background objects and search for a tiny statistical pattern. The signal is weak because the void contains no concentrated object acting like a lens. It is the absence of mass that must be measured. Trying to map a void through lensing is like weighing a missing object by observing how little a floor bends beneath it. The measurement is possible, but it requires precision. Another method studies the motion of galaxies near the void. Galaxies do not move only because the universe expands. They also respond to nearby gravity. A galaxy near a dense cluster falls toward it. A galaxy near the edge of a void tends to move toward the surrounding walls and filaments. By measuring these additional motions, astronomers can estimate how matter is distributed. But distance itself is measured partly through redshift, and motion also affects redshift. This creates a distortion. A galaxy may appear slightly farther away or closer than its true position because of its motion toward or away from us. On a three-dimensional map, structures can become stretched or compressed along our line of sight. A void may appear longer in one direction. A wall may seem thicker. A small internal group may be misplaced. Astronomers must separate the expansion of the universe from the local motion of galaxies. Again, the emptiness is real, but its exact shape is difficult to recover. The gas inside voids is even harder to find. Most ordinary matter in the universe is not locked inside stars. Much of it exists as thin gas between galaxies. In dense regions, gas can become extremely hot and produce X-rays. Inside voids, the gas is cooler, thinner, and more difficult to detect. It may consist of only a few particles within a volume that would contain far more matter on Earth. A spacecraft passing through it would not encounter a visible fog. There would be no cloud to photograph. The atoms might be separated by enormous distances on human scales. Yet across millions of light years, even this thin gas contributes mass. Some of it can be detected when light from a distant object passes through. Specific atoms absorb specific wavelengths. The light arrives with faint missing bands, revealing otherwise invisible material along the path. By examining these absorption patterns, astronomers can search for hydrogen and other elements inside underdense regions. But this method works only when a bright background source lies in the correct direction. The universe must provide a lamp behind the darkness. Without one, the gas remains nearly invisible. This means the interior of the Boötes Void may contain more ordinary matter than its galaxies suggest. Thin hydrogen, warm gas, dark halos, faint dwarf systems. But none of these would make it ordinary. The matter is still spread across a volume so large that the average density remains extremely low. The void may contain hidden objects while remaining a void. There is also a deeper question. What created the original underdensity? The standard answer leads back toward the earliest measurable moments of cosmic history. Before galaxies existed, the universe was filled with hot plasma. Matter and radiation were tightly connected. Tiny variations moved through this plasma as pressure waves. When the universe cooled enough for light to travel freely, those variations were preserved in the cosmic microwave background. This ancient radiation still fills space. Its temperature is almost uniform, but not perfectly. Some directions are slightly warmer, others slightly cooler. The differences are tiny, only a few parts in 100,000. Yet those faint patterns became the seeds of everything. A slightly denser region eventually formed clusters. A slightly less dense region eventually became a void. The Boötes Void may therefore be the mature descendant of a cold underdense fluctuation that existed before the first stars. An imperfection born when the universe was still young enough to glow everywhere. Some theories trace these imperfections even farther back, to inflation. Inflation describes a period of extremely rapid expansion believed to have occurred very early in cosmic history. During this phase, tiny quantum fluctuations may have been stretched to astronomical scales. Variations that began at dimensions smaller than an atom eventually became the starting pattern for galaxies and voids. If this picture is correct, the Great Nothing may have originated from something unimaginably small. A quantum fluctuation expanded by the early universe, then amplified by gravity for billions of years. The emptiness between galaxies may be connected to uncertainty at the smallest scales of reality. This is one of the strangest bridges in modern physics. Quantum behavior may have shaped the cosmic web. The positions of galaxy clusters today may trace fluctuations created before atoms existed. And the Boötes Void, hundreds of millions of light years across, may be the final form of a microscopic shortage of energy or matter in the ancient universe. But inflation does not predict one exact universe. It predicts a range of possible patterns. Most density fluctuations should be modest. Extremely large fluctuations should be rarer. If the Boötes Void began from an unusually deep primordial underdensity, astronomers can ask whether such a fluctuation fits the expected distribution. Perhaps it does. Perhaps it sits near the extreme edge. Or perhaps the void formed not from one extreme fluctuation, but from many smaller ones joining over time. Both possibilities can produce a large underdense region. Determining which history occurred requires mapping the faint structure inside. A single primordial void might appear smoother. A merged complex might contain stronger internal walls and galaxy chains. The few galaxies within Boötes may preserve clues. Their positions are not merely points of light. They are fossils of the void's formation. If they align along narrow filaments, they may mark the remains of boundaries between earlier voids. If they are distributed more randomly, the history may be different. Their ages matter. Their star formation matters. Their chemical composition matters. A galaxy that formed early inside the void tells a different story from one that drifted inward later. Astronomers can study the motion and light of these galaxies to reconstruct where they came from. But reconstruction becomes harder as time passes. Gravity alters orbits. Galaxies merge. Gas is consumed. Stars die. The evidence becomes blurred. The void is ancient, and its earliest history is written only indirectly. Another possibility is that gravity behaves slightly differently across very underdense regions. General relativity has passed every major test performed within the solar system and in many astronomical environments. But cosmology applies gravity across distances far greater than those direct tests. Some alternative theories predict that gravity may be modified in regions where matter is extremely sparse. Dense areas can hide these changes. Voids may reveal them more clearly. If gravity were even slightly stronger or weaker than expected inside underdense regions, voids could grow at different rates. They might become emptier. Their boundaries might move differently. Galaxies near them might show unusual velocities. This makes cosmic voids valuable laboratories. They are places where competing theories can produce different predictions. One model may create many deep voids. Another may create shallower ones. One may move galaxies outward more rapidly. Another may change the lensing signal. By measuring real voids carefully, astronomers can test not only where matter exists, but how gravity behaves where matter is missing. So far, the standard model remains remarkably successful. There is no confirmed evidence that the Boötes Void requires modified gravity, but neither has every detail been measured well enough to close the question completely. The mystery survives because the hardest tests demand information from the faintest environments. Dark energy adds another layer. If dark energy remains constant, voids should continue expanding in a predictable way. If it changes over time, the growth history may differ. Voids respond to the expansion of the universe across enormous scales. Their sizes, shapes, and galaxy motions can therefore contain information about dark energy. A large population of voids becomes more useful than one famous example. Astronomers compare thousands of them. They average their shapes. They study how their sizes change with distance, which also means with cosmic time. They examine how galaxies move around them. They look for tiny effects on background radiation. The Boötes Void captures the imagination because of its size, but scientifically, it belongs to a much larger family. Understanding the family may explain the individual. One subtle effect occurs when ancient microwave radiation passes through an evolving void. A photon entering the void moves through a region with a shallow gravitational potential. As it enters, its energy changes slightly. As it leaves, that energy should be restored if the gravitational structure remains unchanged. But the universe expands while the photon crosses. The void itself evolves. The energy gained and lost may not cancel perfectly. The photon can emerge with a minuscule temperature shift. This is connected to what cosmologists call the integrated Sachs-Wolf effect. The change is extraordinarily small. No human eye could detect it. But across large structures and many measurements, it may leave a faint imprint on the cosmic microwave background. In principle, voids can cast shadows not by blocking light, but by altering its energy through changing gravity. The darkness can leave a temperature fingerprint on radiation older than galaxies. This has led scientists to study whether certain unusually cool areas in the microwave background align with large underdense regions. But such claims are difficult. Signals are weak, structures overlap, chance alignments occur. A void may contribute to a cold region without explaining all of it, and the famous Boötes Void should not automatically be confused with every proposed supervoid connected to microwave anomalies elsewhere in the sky. The universe contains many different voids. Their mysteries can resemble one another without being the same mystery. This distinction is essential. When people hear that an enormous unexplained empty region exists, several cosmic anomalies are often combined into one story. The Boötes Void, the cold spot, local underdensities, giant supervoids detected in galaxy surveys. Each is real as an area of study, but they are not all one object. Some may have ordinary explanations. Some remain debated. Some may result partly from observational limitations. The universe is strange enough without merging separate mysteries into a single imagined whole. The true story is quieter and more difficult. The Boötes Void is not terrifying because scientists have found an impossible force there. It is terrifying because an apparently simple absence requires so many layers of explanation. To understand why a region is empty, we must understand the early universe, quantum fluctuations, inflation, dark matter, galaxy formation, the behavior of gas, the growth of structure, the expansion of space, dark energy, the laws of gravity. One dark region touches nearly every major question in cosmology, and still, there may be no single moment we can identify as its creation. No explosion, no collision, no object that carved it out. The void was not made in one event, it emerged. Slowly, silently, matter moved away. Galaxies failed to form. Smaller underdensities may have merged. The surrounding web became denser. The interior became emptier. Billions of years passed. Eventually, human beings on a distant planet built instruments capable of noticing that something was missing. That may be the most unusual part of the story. The Boötes Void existed long before Earth formed. Its early structure was already developing while the Milky Way was young. The light we now use to map it traveled through space before humans appeared. Yet only recently did intelligence recognize the pattern. For most of history, it was not a named place. It was simply darkness between faint galaxies. Then measurements gave the darkness a shape, a size, a location, a mystery. This is what astronomy often does. It turns absence into an object, silence into data, darkness into structure. The void cannot be photographed like a planet. It has no surface, no color, no central light. Its existence is inferred from the arrangement of everything around. We know it by what is missing. And perhaps this is why a final explanation remains so difficult. Bright objects announce themselves. A star emits light. A galaxy contains billions of visible suns. A black hole reveals itself through surrounding matter. But a void offers almost nothing. Every answer must be built from faint traces, a handful of galaxies, small gravitational distortions, weak absorption lines, subtle motions, tiny temperature effects. The evidence is spread across hundreds of millions of light years. No single telescope can capture the entire truth. The Great Nothing may eventually receive a complete explanation. Its hidden galaxies may be mapped. Its dark matter distribution may be reconstructed. Its internal filaments may emerge. Simulations may reproduce its size and emptiness naturally. What appears impossible today may become an expected result of cosmic evolution. But another possibility remains. The better we map it, the stranger it may become. Perhaps its density is lower than predicted. Perhaps its galaxies move too quickly. Perhaps its shape preserves an unusual primordial fluctuation. Perhaps it reveals something about gravity or dark energy that dense regions concealed. We do not yet know. And until we do, the void remains suspended between two possibilities. It may be an extraordinary example of familiar physics, or a quiet sign that our picture of the universe is incomplete. No monster waits at its center. No visible boundary surrounds it. There may be no single hidden object to discover, only a question spread across an impossible distance. A question made from missing matter. A question that cannot be approached directly because the evidence is almost too faint to see. And the closer astronomers come to explaining the Great Nothing, the more clearly it reveals how much of the universe remains unknown. Imagine that the Milky Way had formed deep inside the Boötes Void, not near its boundary, not beside one of the faint internal filaments, but close to the quietest part of the emptiness. The stars of our own galaxy would still fill the night. Orion would still rise. The planets would still move against familiar constellations. The moon would still cross the sky. Nothing in ordinary human life would reveal that our galaxy occupied one of the loneliest regions in the observable universe. The isolation would become visible only when astronomers looked beyond the Milky Way, and at first they might find almost nothing. The nearest bright galaxies could be so distant that early telescopes would fail to detect them. The sky outside the Milky Way would appear dark and uninterrupted. There might be no Andromeda visible to the naked eye, no nearby galaxy groups offering obvious evidence that our own island of stars was one among billions. For centuries, perhaps longer, the Milky Way could be mistaken for the entire universe. This would not be foolish. It would be a reasonable conclusion based on the evidence available. Science is shaped not only by intelligence, but by location. An observer near a rich galaxy cluster sees a crowded cosmos. Galaxies cover the deep sky. Gravitational interactions are common. Bright clusters provide landmarks across enormous distances. An observer inside a deep void sees something else. A universe that appears sparse, young, perhaps almost empty. The same laws of physics would operate in both places, but the evidence presented to each civilization would be radically different. This raises a disturbing possibility. How much of our own understanding depends on where we happen to live? We do not occupy the center of the Boötes Void. The Milky Way belongs to a small group of galaxies and sits within a larger network of filaments and nearby underdense regions. But even our own cosmic neighborhood is not perfectly average. No location is. Every observer measures the universe from inside some local arrangement of matter. A galaxy near a cluster experiences strong gravitational attraction. A galaxy near a void moves differently. The expansion measured across a small region can appear slightly faster or slower than the cosmic average because local gravity adds motion on top of the general expansion of space. This does not mean the laws of the universe change from place to place. It means the same universal expansion is viewed through a local gravitational landscape. Inside a large void, galaxies tend to move outward toward denser boundaries. An observer measuring only nearby galaxies might interpret some of that motion as faster cosmic expansion. Farther away, once enough of the universe is included, the local effect becomes less important. But a civilization trapped inside an enormous underdensity might need extraordinarily deep observations before recognizing that its local measurements were unusual. Its first map of the universe could be distorted by emptiness. This is another way a void creates isolation, not only physical isolation, but intellectual isolation. The civilization would possess the same mathematics, the same curiosity, the same ability to build telescopes, yet the universe would reveal itself more slowly. The first galaxies beyond its own might appear only as weak smudges. Their light would have traveled for hundreds of millions of years. By the time they were detected, the galaxies themselves would already have changed. The civilization would never see a nearby external galaxy as it truly was in the present. Every object beyond the void would belong to the past. This is true from Earth as well, but inside the emptiness, the delay would become immense, even for the nearest major structures. A neighboring cosmic wall might be visible only through light that began traveling before complex life appeared on the observer's planet. The surrounding universe would be ancient before it was discovered. Astronomers inside the void would eventually find evidence that their galaxy was not alone. They might study the faint glow of distant galaxies. They might detect the cosmic microwave background, the ancient radiation left behind by the hot early universe. That background would be especially important. Even if nearby galaxies were scarce, the microwave glow would still fill the sky. It would reveal that the universe had once been hot, dense, and nearly uniform. Tiny temperature variations would show the seeds from which structure later grew. Through this ancient light, a civilization inside the void could learn that the cosmos extended far beyond its lonely galaxy. The universe would speak to them not through nearby neighbors, but through radiation older than stars. That realization would be profound. Their visible environment would suggest isolation. The microwave background would reveal connection. It would show that the dark space around them had once been part of a glowing whole. Every galaxy, every cluster, every void, all emerging from the same early universe. The Great Nothing is therefore not separate from everything else. It is not a region that failed to participate in cosmic history. It is one result of that history. The void and the galaxy cluster are siblings. One formed where matter gathered, the other where matter was lost. The same initial pattern created both. The same gravity shaped both. The same expansion carried them forward. A void is not outside the universe's architecture. It is one of its largest rooms. Yet living inside that room would be unlike living anywhere familiar. Consider a planet orbiting a star in one of the isolated galaxies of Boötes. Its local galaxy might still contain billions of stars. Some of those stars could host planets. Some planets could contain oceans. The ordinary ingredients of life would not be forbidden, merely because the surrounding cosmic environment was sparse. Within the galaxy, supernovae would create heavy elements. Dust clouds would collapse. New stars would form. Planetary systems would emerge. From the surface of one inhabited world, the night sky might be magnificent. The galaxy's own stars could create a bright band overhead. Nebulae might glow. Nearby planets might be visible. The inhabitants would not feel suspended inside emptiness. Their galaxy would provide everything they considered normal. Only advanced astronomy would reveal the larger truth. Beyond their galaxy, almost nothing was close. Would life be more or less likely in such an environment? The answer is not simple. Void galaxies often experience fewer major collisions. That could make their long-term evolution quieter. A stable spiral galaxy might preserve orderly stellar orbits for billions of years without being violently disturbed by mergers. Planetary systems could avoid some of the chaos associated with crowded clusters. There would be fewer nearby galaxies passing close enough to reshape the disk. Fewer large gravitational disruptions. Fewer encounters capable of triggering intense bursts of star formation and supernova activity across the galaxy. In that sense, isolation could be protective. A calm galaxy may offer stable conditions for life over long periods, but the same isolation can limit growth. Galaxies in voids receive less gas from surrounding structures. They have fewer opportunities to merge with other systems. They may remain smaller. Their rate of star formation may decline earlier if fresh material becomes scarce. Some void galaxies appear rich in gas and continue producing stars, while others may evolve slowly and faintly. The environment does not determine one destiny. It changes the probabilities. Life inside a void might develop in a quiet galaxy, but it would inherit an almost impossible distance from everything beyond it. If intelligence emerged there, its civilization could expand through its own galaxy. Given enough time, it might reach neighboring stars. Then, more distant systems. It could build habitats, send probes, reshape planets, perhaps spread across tens of thousands of light years. From the perspective of a single world, this would be an unimaginable achievement. But from the perspective of the void, the civilization would barely have moved. Its entire galactic expansion would occupy a point inside the surrounding emptiness. Even a society controlling every star in its galaxy would remain separated from the next major galaxy by millions or tens of millions of light years. The limits would no longer be technological in the ordinary sense. They would be geometric. A spacecraft moving at 10% of the speed of light would be astonishing by human standards. It could cross the Milky Way in roughly 1 million years. But crossing 100 million light years would take 1 billion years. 1 billion years inside a spacecraft is not a journey. It is a geological era. Stars change during that time. Planets lose atmospheres. Galaxies evolve. The universe expands. The destination moves farther away while the traveler approaches. Even a machine designed to repair itself, reproduce, and continue indefinitely would face cosmic radiation, collisions with particles, mechanical degradation, and the eventual exhaustion of usable energy. The void is too large for travel to feel like travel. It becomes migration across cosmic time. A civilization attempting it would not send passengers expecting to arrive. It would send a process. Machines building machines. Habitats creating new habitats. Generations emerging and disappearing inside artificial worlds. The mission's original language might be forgotten before the opposite wall was reached. The civilization arriving would no longer be the one that departed. The void would transform travel into evolution. This is why the Great Nothing feels like a barrier despite containing no wall. Nothing blocks the path. There is no storm, no field of debris, no gravitational trap, only distance. Yet distance alone can be stronger than any physical obstacle. A wall can be broken, a mountain can be crossed, a planet can be escaped, but hundreds of millions of light years cannot be negotiated through courage. The universe does not care how determined the traveler is. The light speed limit remains, time remains, expansion remains. The emptiness wins by being large, and it grows. The cosmic web is not frozen. As the universe continues expanding, gravitationally bound systems remain together. Stars stay inside galaxies. Galaxies within some groups and clusters remain connected by gravity, but structures separated by sufficiently large distances continue moving apart. Dark energy appears to accelerate this process. Over the distant future, galaxies beyond local gravitationally bound regions will recede faster and faster. Their light will become increasingly redshifted. They will grow dimmer. Eventually, many will pass beyond the cosmic horizon, not because they move through space faster than light nearby, but because the space between distant regions expands. Once a galaxy crosses that horizon, light emitted from it will never reach the observer. It is not merely too faint. It becomes causally disconnected. This future will make every surviving civilization resemble one living inside a cosmic void. Distant clusters will disappear from view. The cosmic web will fade. Only the local group of gravitationally bound galaxies will remain visible. Far future astronomers may look into the sky and see one enormous merged galaxy surrounded by darkness. They could conclude that the universe is static and nearly empty. The evidence of expansion would become difficult to recover. The cosmic microwave background would stretch to wavelengths so long and energies so weak that detecting it might be nearly impossible. The light elements created in the early universe would remain, but their history could be misunderstood. The great discovery that the universe began in a hot, dense state may become inaccessible to observers born too late. The Boötes Void offers a preview of this future. It shows what the cosmos looks like when visible structure becomes distant, when islands of matter are separated by expanding darkness, when the universe is present, but no longer close. Perhaps that is the true terror of the void. It is not only an unusual place, it is a destination toward which the entire observable universe may be moving. Not spatially. Temporally, the far future may belong to isolation. Galaxies once visible across the sky will vanish beyond horizons. Civilizations will inherit smaller observable universes than we possess today. They may know less about cosmic history despite having more advanced technology. Information can disappear without being destroyed. It only needs to move beyond reach. We live during an unusual period. The universe is old enough for galaxies, heavy elements, planets, and life to exist, but it is still young enough for distant cosmic structure to remain visible. We can observe galaxies billions of light years away. We can map filaments. We can study voids. We can detect the ancient background radiation. The universe has not yet hidden most of its history. A civilization inside Boötes would begin with less information. A civilization in the distant future may face the same limitation everywhere. This makes our present view valuable. The sky is not only beautiful, it is temporary evidence. Every distant galaxy is a message that will not remain visible forever. Every cluster is part of a map future observers may lose. Every void reveals the shape of matter, before expansion separates the structures beyond contact. The Boötes Void appears like missing information in that map. Yet by studying it, astronomers gain information about almost everything else. Its boundaries reveal where matter moved. Its internal galaxies reveal how structures grow in isolation. Its lensing effects reveal the distribution of dark matter. Its expansion helps test dark energy. Its shape preserves traces of the early universe. The void is defined by absence, but scientifically, it is full of evidence. There may also be a strange advantage to observing the universe from within one. A galaxy inside a deep void would experience less interference from surrounding structures. The gravitational environment would be simpler. There would be fewer bright foreground galaxies obscuring more distant objects in some directions. An advanced civilization might use the quiet sky to make extremely precise measurements of ancient radiation. Its local environment would be lonely but clean. The very absence that delays discovery could eventually allow delicate observations. A void is not merely a prison, it is also a laboratory. Its simplicity strips away some of the noise of crowded regions. This is why astronomers value underdense space. Clusters show what gravity builds when matter is abundant. Voids show how the universe behaves when gravity has less material to work with. Both are necessary. Studying only clusters would be like studying a landscape by looking only at mountains. The valleys matter too. Their depths reveal how high the mountains truly are. Their shape reveals how the terrain formed. Cosmic voids are the valleys of the universe. But the Boötes Void may be more like an entire inland sea emptied of water. Its boundaries are so distant that the interior feels disconnected from the web surrounding it. Could an observer at its center even identify the nearest boundary? With sufficiently powerful instruments, yes, galaxies on the surrounding walls would appear concentrated in certain directions and redshift ranges. Their three-dimensional positions could be reconstructed. But no single image would reveal the complete shape. The observer would need to build the void piece by piece, measure one galaxy, then another, estimate distances, correct for motion, search for faint systems. The full emptiness would exist only inside the map. This is true for us as well. No telescope has photographed the Boötes Void as one giant black sphere. Images that seem to show such a cavity are visualizations, reconstructions, ways of translating data into a form the human mind can understand. The real void is experienced through numbers, coordinates, redshifts, density estimates. Its terror is mathematical before it becomes emotional. A blank region in a three-dimensional survey. A place where thousands of expected galaxies fail to appear. The mind then tries to fill that absence with an image, a black ocean, a hollow sphere, a cosmic wound. But none of these are quite correct. The void has no surface. Light crosses it. Radiation fills it. Galaxies beyond it remain visible through it. If you approached from outside, you might not notice the moment you entered. Only after traveling for millions of years would you understand that nothing nearby was replacing what had fallen behind. The absence would reveal itself slowly, one galaxy disappearing, then another, the distance to the nearest light increasing, the background remaining, but the foreground becoming empty. A traveler might continue expecting the next galaxy to appear. 1 million years, 10 million, 50 million. Still the emptiness would continue. There is something deeply unsettling about an environment that does not announce its danger. A black hole reveals itself through intense gravity and hot surrounding matter. A star announces itself with light. A supernova tears across space with energy. The void does almost nothing. It does not attack, it does not pull, it does not burn. It simply removes the possibility of arrival. The farther you go, the more difficult return becomes. The point of departure fades. The destination remains unimaginably distant. The traveler becomes surrounded by the consequences of scale. And yet, the Boötes Void is still part of the same universe as Earth. The same physical constants apply there. Atoms behave the same way. Light travels at the same speed. Gravity follows the same equations. A human spacecraft entering the void would not encounter exotic physics merely because galaxies were scarce. The terror is not that nature changes. It is that nature remains perfectly ordinary across a distance human beings cannot comprehend. The universe does not need monsters to become frightening. It only needs enough space. A few galaxies may float inside boats like islands. Around one of their stars, a planet may be turning now. Perhaps lifeless, perhaps covered in oceans, perhaps holding organisms that will never become intelligent. Or perhaps somewhere inside that darkness, another civilization is looking outward. Its astronomers mapping faint lights along the distant boundary. Its philosophers wondering why their galaxy seems abandoned. Its engineers calculating whether the gap can ever be crossed. They may not know that Earth exists. Even if they sent a signal directly toward us, the message could require hundreds of millions of years to arrive. It might already be traveling, a radio wave weakened by distance, a deliberate pattern crossing the emptiness long after its creators disappeared. We would not hear a voice. We would receive history. The void makes every message ancient, every observation delayed, every connection one-sided. It separates not only places, but moments. This is what makes the Great Nothing more than an empty region. It is a machine for turning the present into the past before anyone else can see it. A civilization lives, creates, looks outward, sends light, then changes or vanishes. Millions of years later, another civilization receives the first image. The two may exist in the same universe without ever sharing the same age. Cosmic distance makes contemporaries impossible, and inside a void, that separation becomes extreme. The Boötes Void may have formed through familiar processes. Its hidden structure may eventually be mapped. Its size may prove statistically rare but completely natural. The apparent mystery may slowly dissolve. But explanation will not make it smaller. Understanding how the emptiness formed will not make crossing it easier. Knowing that gravity and expansion created the void will not remove the isolation it imposes. Some mysteries become less frightening when explained. This one may become more frightening. Because the final answer could be ordinary. No catastrophic event. No secret object, no break in physics, only a region that began slightly emptier than its surroundings and was given enough time to become almost unimaginably alone. The Great Nothing may have no monster hidden inside it. The Great Nothing may be the monster, not because it destroys whatever enters, but because it places everything so far apart that destruction is no longer necessary. Nothing can reach you. Nothing can answer. Nothing changes the horizon. The darkness simply continues. And as the universe grows older, more of the cosmos may begin to look the same. The most honest answer may also be the least dramatic. The Boötes Void was probably not created by a single impossible event. No hidden explosion tore galaxies from space. No unknown object swallowed a region hundreds of millions of light years across. No visible boundary separates ordinary reality from something beyond physics. The void may have formed slowly, from small differences in the early distribution of matter. from gravity drawing material towards surrounding filaments, from smaller underdense regions expanding and merging, from billions of years during which very little matter remained available to form bright galaxies. This explanation is reasonable. It fits the broad structure of modern cosmology, and yet something remains unresolved. Not whether cosmic voids can exist. They clearly can. Not whether gravity can create enormous empty regions. It clearly does. The remaining mystery is why this particular region became so large, how empty it truly is, and whether its full structure can be reproduced naturally from the conditions we believe existed in the early universe. The Boötes Void sits near the boundary between explanation and uncertainty. We understand the processes. We do not yet understand every result. That distinction matters. Science rarely moves from complete ignorance to complete certainty in a single step. More often, the shape of the answer appears first, then the details resist. A theory explains most of what is seen. Measurements improve. New exceptions appear. Definitions change. The object becomes less mysterious in one way and more complicated in another. The great nothing may follow this pattern. Future surveys may reveal thousands of faint galaxies within it, not enough to erase the void, but enough to show that its interior contains a delicate web. Astronomers may map dark matter through gravitational lensing. They may detect thin gas through absorption in distant light. They may reconstruct the motion of galaxies along the boundary. Simulations may eventually produce structures with the same size, density, and internal arrangement. If that happens, the famous mystery will not vanish entirely. It will transform. The question will no longer be how the void could exist. The question will become what the void teaches us about the universe that created it. Because an explanation does not make the great nothing ordinary. It makes the universe capable of creating something extraordinary through ordinary laws. That may be even more unsettling. A region hundreds of millions of light years across does not require a cosmic disaster. It may need only a tiny shortage of matter and time. A slight imbalance becomes a gap. The gap expands. Matter drifts toward denser surroundings. Galaxies fail to grow. Small voids join. The cosmic web sharpens around them. And after billions of years, the result is a darkness large enough that light itself needs an age of worlds to cross it. No violence is necessary. No intention. No single moment of creation. Only gravity repeating the same simple behavior across unimaginable time. The great nothing is the final shape of a small beginning. This should make us reconsider what counts as powerful. Human beings associate power with energy, a bright star, a supernova, a black hole, a collision between galaxies. But absence can shape the universe too. A void influences motion because it contains less gravity than its surroundings. Matter leaves it. Galaxies gather along its walls. The distribution of everything visible is partly determined by what is missing. The void has no hand, no surface, no central engine. Yet its emptiness becomes part of the architecture of space. This is one of the deepest lessons of the cosmic web. Structure is created by contrast. A filament appears dense because a void surrounds it. A cluster appears bright because darkness lies between clusters. The universe does not consist only of objects. It consists of relationships between objects and absence, between concentration and emptiness, between the places where gravity succeeded in gathering matter and the places it did not. The Boötes Void represents one extreme of that contrast. To us, it feels unnatural because our existence depends upon concentration. Life requires matter gathered closely enough to form stars. Stars require gas gathered inside gravitational wells. Planets require heavy elements created and collected over generations. Bodies, oceans, atmospheres, and cities all depend upon material being brought together. We are creatures of density. We live on a solid world beside a star inside a galaxy. Every part of our environment teaches us that something should be nearby. A floor, a horizon, a light, a destination. Cosmic voids remove those expectations. They reveal how rare concentration is when compared with the full volume of space. Most of the universe is not made from places like Earth. Most of it does not contain stars. Most of it does not contain galaxies at ordinary separations. Most of it is distance. The luminous universe occupies the threads. The darkness occupies almost everything between them. From Earth, stars dominate our emotional image of the cosmos because they are what we can see. But visibility is not the same as volume. The bright universe is a skeleton suspended inside emptiness. The Boötes Void allows us to feel that truth. Perhaps this is why it seems more frightening than a black hole. A black hole is concentrated. It has a location. A boundary can be defined. Its gravity becomes stronger as you approach. You know where the danger is. A void has no central point that feels dangerous. Its entire scale is the danger. There is no edge close enough to escape toward, no object to avoid, no force to fight. Only the realization that every possible destination is too far away. The emptiness does not threaten through destruction. It threatens through disconnection. A civilization within one of its galaxies might survive for millions of years. It could become advanced, peaceful, powerful. It could reshape planets and travel between stars. Yet from the perspective of the wider universe, it would remain almost completely alone. Its achievements could fill a galaxy and still fail to cross the surrounding dark. Its brightest signals would weaken while traveling outward. Its messages would move at light speed and still need millions of years to approach another major structure. The civilization could speak into the universe, but no reply would belong to the same generation. Perhaps no reply would belong to the same species. Communication across such a distance is not conversation. It is archaeology sent forward. Each message becomes a fossil of the civilization that created it. A pattern traveling after the hands that made it are gone. This raises a quiet possibility. Signals could already be crossing cosmic voids. Not only the Boötes Void, all of them. Light from distant civilizations, if any exist, could be traveling through underdense space now. Some signals may have been sent before Earth formed. Some may not arrive until the sun has changed beyond recognition. There could be messages moving between galaxies whose senders and receivers will never coexist. The universe may contain communication that can never become dialogue. This is not evidence that such civilizations exist. It is simply a consequence of scale. If intelligence appears in isolated places, distance determines what connection means. From Earth, the silence of space is often discussed as a mystery. Why have we not heard anyone? But cosmic voids reveal one answer that requires no absence of life. The universe is large enough to hide life through delay alone. A civilization may transmit, another may listen. Yet their signals miss one another by millions of years. The silence may not mean nobody spoke. It may mean the words are still traveling, or that they passed before anyone was ready to hear them. Inside a void, this possibility becomes almost unavoidable. Distance separates not only locations, it separates eras. The same thought applies to our observations. Every galaxy we see inside the Boötes Void is ancient. We do not know what exists there now. A faint galaxy may have merged with another. Its stars may have changed. New planets may have formed. A civilization could have appeared after the light began its journey toward us. It could have risen and vanished while its galaxy's older image was still crossing space. When we look into the void, we do not inspect the present. We inspect layers of past time. The emptiness itself is delayed. What appears quiet may no longer be quiet. What appears unchanged may have evolved for hundreds of millions of years. Astronomy teaches humility through this delay. We never see the distant universe as one complete moment. There is no universal photograph of now available to us. Near objects are seen recently. Distant objects are seen long ago. The deeper we look, the farther backward we travel. The sky is not a map of space alone. It is a map of different times placed beside one another. The Boötes Void occupies an enormous region within that map. Its near edge and far edge are not seen at the same age. Light from the far side began traveling earlier. The structure we reconstruct is assembled from pieces belonging to different moments. We speak of the void as one object, but observationally, it is a history, a changing region frozen into layers of arriving light. Future instruments will improve this reconstruction. Larger telescopes will detect fainter galaxies. Wider surveys will map enormous volumes with greater precision. Radio telescopes may trace neutral hydrogen too dim to appear invisible light. X-ray and ultraviolet observations may reveal thin gas. Gravitational lensing may map invisible matter. Computers will compare the data with simulations containing trillions of particles and increasingly realistic galaxies. Artificial intelligence may identify patterns too subtle for human observers. The great nothing will become less blank. Its internal structure will emerge. Perhaps astronomers will discover that it contains a chain of dwarf galaxies crossing its center. Perhaps several weak walls will reveal that the void formed from smaller regions. Perhaps its dark matter distribution will match the standard model beautifully. Or perhaps measurements will refuse to cooperate. The void may remain too empty. Its galaxies may move differently from predictions. Its gravitational signal may suggest an unexpected distribution of matter. A small discrepancy could survive every correction. And a region known for containing almost nothing could become the place where something new is discovered. This is the promise hidden inside cosmic emptiness. Dense regions contain many interacting processes: mergers, hot gas, black holes, star formation, explosions. Their complexity can hide subtle effects. Voids are simpler. There is less matter, less activity, fewer overlapping structures. If gravity changes slightly under very low density conditions, voids may reveal it. If dark energy behaves differently across time, void growth may record that change. If dark matter has properties beyond those assumed in standard simulations, the distribution of faint structures may expose them. The emptiest places can become the cleanest tests. This may be why the Boötes Void will remain scientifically valuable even after its formation is explained. It is not merely an anomaly to be solved. It is an experiment created by the universe, a laboratory hundreds of millions of light years wide, one in which matter was removed from the center and placed along the edges, one in which the expansion of space can act with less resistance from gravity, one in which galaxies evolve without crowded neighbors. a laboratory no civilization could build, only observe. The void also changes how we think about cosmic importance. Human instinct places importance where something happens. A star is important because it shines. A galaxy is important because it contains stars. A cluster is important because it gathers galaxies. The void appears secondary, a gap left between the real structures. But the cosmic web could not be understood without it. The walls and filaments formed partly because matter moved out of underdense regions. The voids helped create the concentrations. The absence and the structure developed together. You cannot tell the history of one without the other. The Great Nothing is therefore not outside the story of creation. It is one of creation's results. The early universe did not only build, it separated. It gathered matter into some places and left other places increasingly bare. Creation on cosmic scales includes emptiness. This may sound contradictory, but nature often works through difference. Stars form because cold gas becomes denser than its surroundings. Weather forms because pressure and temperature vary. Ocean currents form because energy is distributed unevenly. Life itself depends upon gradients. Differences create motion. The cosmic web is the largest expression of this principle. Matter flows from low-density regions toward high-density structures. Voids grow, filaments strengthen, galaxies gather. The universe's shape emerges from imbalance, and somewhere inside that vast pattern, Earth formed. Our planet exists because matter did not remain evenly spread. If the early universe had been perfectly smooth, gravity would have had no denser regions to amplify. No galaxies would have formed, no stars, no planets, no observers. The same imperfections that created the void also created us. This creates an unexpected connection. The Boötes Void feels hostile to life because it is so empty, but its existence belongs to the same process that made life possible elsewhere. The universe needed unevenness. Some regions had to become dense, others inevitably became sparse. The cosmic architecture that produced Earth also produced the Great Nothing. We are opposite outcomes of one ancient pattern, a planet filled with life and a region almost without galaxies. Both trace back to tiny fluctuations in the early universe. Both are part of the same history. This connection makes the void feel less alien, not less frightening, but less separate. Its darkness is related to our light. Matter that did not remain there contributed to structures elsewhere. The surrounding walls grew richer as the interior became poorer. Nothing in the cosmic web evolves alone. Even isolation is created through relationship. The Boötes Void may appear disconnected now, but its history is written into the galaxies around it. Their locations define its boundaries. Their motions reveal its gravity. Their density shows what the interior lost. The void is known through the light surrounding it. This is perhaps the most poetic fact about it. We cannot see the Great Nothing directly. We see everything that is not there. We map the absence by measuring light. A galaxy appears, then another, then a long distance with almost none. The pattern becomes a structure. The lack becomes a discovery. The darkness receives a name. There is something deeply human about this. We are able to notice not only objects, but missing objects, not only sound, but silence, not only presence, but absence. The void exists physically whether anyone recognizes it or not. But its mystery exists because a mind compared expectation with observation and realized that something was missing. Astronomy is filled with such discoveries. Invisible planets inferred from motion. dark matter inferred from gravity, black holes inferred from surrounding light, dark energy inferred from expansion, voids inferred from the absence of galaxies. Much of the universe becomes known indirectly. We rarely touch the answer. We observe effects, we build models, we test them. Reality reveals itself through consequences. The Great Nothing may therefore be the perfect symbol for modern cosmology. It is vast, mostly invisible, difficult to define, connected to dark matter and dark energy, seen only in ancient light, partly understood, still uncertain. It reminds us that knowledge does not always arrive as a clear image. Sometimes knowledge is a blank region in a map, a deviation in a graph, a missing population, a silence that appears too large to be accidental. Tonight, as the universe grows quiet around you, imagine the scale of that silence. Imagine leaving the Milky Way, passing beyond the nearby galaxies, crossing the filaments of the cosmic web, watching the lights behind you gather into a distant wall. Ahead lies the void. At first, it does not seem different. Space remains black, stars remain distant, but the journey continues. 1,000,000 years, 10 million. The nearest galaxies fade. The surrounding structures become thin arcs of light far behind. Nothing replaces them. The spacecraft moves forward, but the darkness does not change. There is no destination growing larger, no new cluster rising ahead, only ancient background galaxies, faint and unreachable, shining through the emptiness from beyond. The traveler continues. Entire species evolve on distant worlds. Stars exhaust their fuel. New stars ignite. Galaxies slowly change shape. Still, the crossing is incomplete. The void is not a place measured by journeys. It is measured by cosmic history. A person cannot cross it. A civilization may not cross it. Light barely crosses it within the lifetime of complex life on Earth. This is what scale means in the universe. Not simply something large. Something so large that familiar ideas stop functioning. Travel becomes evolution. Communication becomes archaeology. Observation becomes history. Distance becomes isolation. The Boötes Void may one day have a complete explanation. Its galaxies may be counted, its dark matter mapped, its formation reproduced inside simulations. The phrase "has no explanation" may no longer be accurate, but the deeper truth will remain. We may explain how the void formed, without ever making its size emotionally understandable. Science can place numbers around it, hundreds of millions of light years, a certain average density, a certain number of galaxies, a measured redshift, a calculated probability. But numbers do not fully capture what it means for emptiness to extend that far. The human mind can understand the definition. It cannot experience the scale. Perhaps this is why the Great Nothing will always feel mysterious. Not because nature refuses to explain it, but because reality exceeds the imagination trying to hold it. We evolved to understand footsteps, seasons, mountains, rivers, the distance to shelter, the time until sunrise. We did not evolve to understand a region that light needs hundreds of millions of years to cross. The universe is not obligated to fit inside the instincts of one species on one small planet, and cosmic voids make that clear. They remove the familiar objects that usually help us measure space. No nearby stars, no bright landmarks, no horizon, only distance without reference. Emptiness becomes its own scale. So what is the most terrifying void in the universe? It is not necessarily a supernatural mystery. It is not a hole outside reality. It is not evidence that part of space has been erased. It is a region where the universe began with less matter, and gravity made that shortage enormous. A place where galaxies became rare, where distance became dominant, where anything living inside could remain isolated beyond all reasonable hope of contact. Its explanation may be hidden in the earliest fluctuations of the cosmos. Its details may be waiting inside faint galaxies and invisible dark matter. But its emotional power comes from something simpler. The void shows us that the universe does not need to be violent to become terrifying. It can become terrifying through silence, through time, through scale, through the absence of anything close enough to reach. And perhaps somewhere inside that darkness, a star is shining tonight. A planet is turning around it. Clouds are moving across an unknown sky. Something may be looking upward, not seeing Earth, not seeing the Milky Way, only distant points of light scattered along the edge of an enormous black universe. Perhaps it wonders whether anything exists beyond its galaxy. Perhaps it believes it is alone. Perhaps its astronomers have just detected the first faint galaxy outside their own. A barely visible smudge, a small proof that the darkness does not continue forever. They may never reach it. They may never speak to anyone there. But knowing that it exists could change them, just as knowing about the Boötes Void changes us. It reminds us that our crowded sky is not guaranteed, that our cosmic neighborhood is a kind of fortune, that galaxies, stars, and worlds are islands inside something far larger and darker, and that every light we see is valuable because so much of the universe contains almost none. As you drift towards sleep, let the scale slowly fade, from the void to the cosmic web, to the Milky Way, to the solar system, to Earth, to the quiet room around you. The universe is unimaginably large, but you are not floating at the center of the great nothing. You are here, on a world filled with oceans, air, warmth, sound, and life. Beneath a sky carrying light from distant stars, inside a galaxy surrounded by other galaxies. For one brief moment in cosmic history, we can see the universe while much of it is still visible. We can map its bright filaments. We can measure its empty regions. We can ask why the darkness formed, and although we do not yet know every answer, the questions themselves connect us to the cosmos. The great nothing remains far away, silent, expanding, holding its few galaxies inside an ocean of distance, perhaps fully explainable, perhaps still hiding something unexpected, but forever reminding us of the same quiet truth. The universe is not mostly made from stars. It is mostly made from the darkness between them. Good night.